I will speak about Archean time, and just I will speak mainly about continental crust. And if you look on the amount of papers published on this topic about the Archean crust, you can see that more and more people are interested, or at least published, on this domain. So each year there is about 80 papers related to the genesis of the Archean crust. So this is there are more and more papers about this topic. So you remember this? So this morning I spoke about this period. That was quite pleasant because there were no rock for constraining the assumption. But now, as we will look in the Archean, we have rocks. So we will need to, we can base our arguments on the composition of these rocks. So first, some pictures from my holidays. And for instance, if you want to see old rocks, so you can go to the room just nearby. Or if you want to walk during 1 or 2 days on these rocks, you can go in Greenland, in Amitsok area. So there are some plutonic rocks, which are 3.82 billion years old. And they are coming from here. Isua and Amitsok are somewhere here in southwest Greenland. And the rocks are gray gneisses with a very strong foliation, you can see here. And they are cut by younger granite here. Now, if you only want to walk during few hours on outcrops, so in other words, if you want smaller outcrops, still in Greenland, in Isua, but you can find some sedimentary rocks, which are 45 years older. And these rocks are Isua gneisses. And as you can see here, you can see a banding, that is a sedimentary banding in this rock. So these rocks obviously are sedimentary, but you can see on each side amphibolite, so black amphibolite this time, here and here, and these amphibolite are basalt, metamorphosed basalt. So these rocks are in fact supracrustal rocks. Supracrustal means emplaced at the surface of the earth. That can be sediments or that can be lava, but emplaced at the surface of the earth. And of course, the oldest one, you can go to Canada, but as we have seen this morning, this is something very small. And you remember, we have seen this morning. I will not comment more about these rocks. So, what is interesting in studying the Archean crust? So here are different propositions for the quite recent ones about the amount of crust generated in course of time from the Archean to present day. And what we can see is that, well, these models are not exactly the same. There are differences. But in fact, what is important for us is this point, is that if we look at 2.5 billion years, so at the end of the Archean, so here is the end of the Archean, and we can see that between 3/4 and 2/3 of the continental crust, of the present-day continental crust, was generated at the end of the Archean. So 75% of the continental crust has been generated during Archean and Archean times. So this is something important. That means that the first half of the Earth's history was the very strong period of extraction of the continental crust from the mantle, a very strong period of genesis of this continental crust. So this is the first point, and this is the reason why this period can be interesting. So if we want to, you recognize this is a map of the world on Earth, and if you want to have Archean rocks, here in red are the places where Archean rocks outcrop. And in yellow, these are places where we have Archean crust under a small sedimentary cover, just like, for instance, the Hercynian belt is under the Paris basin. You can find old rocks. So under sedimentary cover, you can find these Archean rocks. And you see that they form some big shields, or cratons. And of course, close to us is a Baltic shield and Ukrainian shield here. But there is in Siberia, the Sino-Korean shield, Indian, Australian, Antarctic, South Africa, West Africa, South America, North America. And in fact, if we consider that the Earth is a living planet with a lot of erosion and plate tectonics, this is a very big amount of Archean crust that remains after 2.5 million years of erosion and so on and so on. So we still remain huge volumes of this Archean crust. I suppose you recognize this. This is Australia. And if we look at this region that is called the Pilbara area in northwest Australia, so here is a satellite view. So you have the scale here, and maybe the city of Portland is somewhere here. What we see, first we can, on this photo, we can eliminate the rocks that are not Archean in age. So, okay, here are only the Archean rocks. In yellow, here are some potato-shaped granitic rocks, which is called is granite and gneiss. This is called granitognesic rocks. Covering these rocks are sediments and volcanic rocks that are called greenstone belts, and belts due to the shape, due to the elongated shape we can find in some places. And after this greenstone, we have what we call late granites that cut both the basement and the greenstone belts. Okay, this is the situation in Australia. Now, South Africa. So we are here in South Africa, here, and Swaziland, here. And what we can see is that we have the same three components. In yellow, the granitognesic basement, color green and brown, the greenstone belt. Here, this is the Barberton greenstone belt. And in red, the late granite, cutting everything. You like the maps, I expect? Here we have the same. So the basement, granitognesic basement in yellow, greenstone belt in green, and late granite here in red. With one granite that is very famous is called the crustal granite. It is 20 kilometer wide, 400 kilometer long, and the thickness is more than 20 kilometers. And when we say that it is 400 kilometers long, in fact it disappears under the Deccan traps, and maybe it is longer. So it's a very huge body of granitic rocks. The same in Karelia, or in Western Europe. So we have the basement in yellow, the greenstone belt here in Finland or here in Russia, and the late granite. And here the same in Greenland. The petrogenesis, some belts, just like Isua belt and late granite. So what I would like to say is that everywhere in the world, I could have put more maps, but we will see exactly the same thing. The Archean crust is made up of three main components: a granitognesic basement, supracrustal rocks that form the greenstone belts, and late granite. And you can find this everywhere in the world. So this is the same in all the cratons. We have the same succession and the same three main lithologies. So now some pictures. Something quite boring. The grey gneisses. So you have seen yesterday a sample of this gneisses, of Abitstock gneisses. So they are with a strong foliation, grey gneisses. Maybe you remember there was a very nice slice of the ancient gneiss complex from Swaziland, and with layers, white and black layers. So it is coming from this outcrop, and you can see here this gneisses, this grey gneisses with strong foliation, and a lot of granitic veins cutting this. The same here in a show in Australia, 3.4 billion years old. Here, more complicated outcrop, but the same pictures. We have the peninsular gneisses in South India. So grey gneisses here with a strong foliation and cut by granite and basaltic veins here in black. The same in Brazil, here. The same in Kola Peninsula in Russia with, granitic vein here and with a basaltic vein, but the gneisses are here. And finally, in some places, just like here, in the young gneisses of Narvala in Finland, we have homogeneous gneisses. Okay. Why did I show you so many pictures of this if they are everywhere the same? And I hope that you are convinced that everywhere in the world these gneisses are gray gneisses and the same in all places. So if you have seen this kind of gneisses in one place, it's not necessary to buy an air ticket to go in another part of the world. This is exactly the same. But this has some implication because this corresponds to extremely huge volumes of granite. And in a few minutes, when we will try to discuss the genesis of these rocks, of course, it will not be possible to imagine a process that can work in one place but not in another one and so on. We should have to build a very robust and very solid model that can work everywhere in the world during more than 1.5 billion years and produce always the same kind of rocks. So the implication of this is we need to have a very general process in order to generate this kind of rocks. If now we look at the Greenstone belt, we have there are more different kind of rocks. For instance, here we have lava. So the Greenstone belt, as I told you, are supracrustal rocks. So lava and placed at the surface and sediments. If we look at the lava, we have this kind of lava. These rocks are komatiite. So this is a pillow lava and placed under water. And these rocks are komatiite. This komatiite, we will discuss their genesis later, but these komatiite are ultramafic magma. And this kind of rocks, the Earth today do not know or is not able to produce this kind of magma. These magmas are known only during the Archean times. After Archean, the Earth is unable to generate this kind of magma. In addition, these komatiite have very special textures that you have seen certainly yesterday with needles of olivine here in the rocks, and this texture is called spinifex texture. Associated to this lava, there are basic magma, just like basalt. These are tritic basalt, with pillow texture here too. And maybe you understand why we call these rocks greenstone belts, because the color is green due to the metamorphism of these rocks. So these are basalt, pillow, here also pillow from Isua. So the pillows are deformed, as you can see here. And also, in very rare occasion, we can find intermediate to acid lava, just like a dacite here. This is a dacitic tuff. But what you must remember is that the volcanism in this greenstone is mainly basic and ultra-basic. And there is very few intermediate to acid rocks. There are almost no, for instance, no andesite. Why today in subduction zones there is a lot of andesite. During Archean there is almost no andesite, but mafic and ultramafic rocks. Now if we look at the sediments, we have detrital sediments, just like your growackies, with a bonding corresponding to layers, to sedimentary layers with different composition. We can find conglomerates, like here, with very big boulders. And some sandstones. Here is a sandstone with sedimentary pictures, as you can see here. And in fact, this picture are extremely well preserved, such as some people, specialists of this sedimentary feature, studies this, and they can demonstrate that this structure are due to tide. So this is the effect of tide on these sediments. So they study the tide, and they show that there is some rhythmicity, And they evaluate that the duration of a moon cycle was of 20 days, when it is of 28 or 27.5 days today. And so the conclusion is that the moon was close or closer to the Earth at that time. And as the moon was closer to the Earth at that time, some people predict tides of 100 meters. Sea tide, not continental tide, so which is something very important. So I just speak about this to say that the preservation of these sediments is exceptional when we think that these sediments are 3.1 billion years old. We can find also in this kind of environment ribbon marks and some mud cracks. These are mud cracks. And of course, these mud cracks indicate that some part at least of the continent will emerge, because we need to have evaporation of water in order to produce this kind of feature. And so there were at least some parts of the continent that will emerge. Another kind of sediments restricted to Archean and beginning of Proterozoic are the banded iron formation, called BIF for banded iron formation. So these are some shells due to the precipitation of element in solution in water. So there are precipitation of silica in white, and here this is iron oxide in black. So here this is one from Finland. There are, for instance, this one that are coming from Sandur in South India. This level, where you have seen, I suppose, sample yesterday, coming from Goping Gap in Australia, and this one, here, I show you a picture from Isua. So, I will not speak about this, but this kind of BIF are used to prove the absence of oxygen in the atmosphere during Archean times. Because we can form this only if the atmosphere and the ocean are not oxidizing, but reduced environments. Just a word to say that now about 90% or more of iron ore are coming from this kind of banded iron formation. So most of the iron used today is coming from this kind of banded iron formation, and here is a picture of a mine in Pilbara in Australia. Other kind of sediments, special in the Archean, are chert. So this is mainly hydrothermal silica that precipitated in an environment, probably just like black smoker or white smoker along the mid-ocean ridge. And here, for instance, is one of these bar of chert in Australia. And as you can see, the chert is not a simple rock. It can have a quite difficult history. We have here some deposit of red chert, broken, and now deposit of green one, and so on. So the story can be quite complicated. But something you must remember is that in this Archean time, the amount of chert was by far more important than today. And if you look here at this North Pole in Australia, there is a lot of chert. All these rocks are chert. And the amount of chert is more important than today. Clearly more important. What else? So probably traces of life. This is a stromatolite from North Pole in Australia, 3.4 billion years. So we have nice small stromatolite here. And of course, in more recent rocks, we have this stromatolite at 2.7 in Tumbiana in Australia. Now, just a look at the late granite. So the late granite, we can see here one of these late granite cutting the greenstones. And this is a granite, but this is very special granite. As you have seen on the sample yesterday, it contains big crystals of car feldspar here, and it is quite dark. The color is dark due to the big amount of biotite and amphibole. And here is another sample. So you can see this is a very dark rock, but with phenocryst of K-feldspar. The same here from, this is the granite, the huge batholith in India, dark rock with K-feldspar. And here from the Limpopo between Zimbabwe and South Africa, and you have also a lot of K-feldspar in a black matrix here. I will not have time to discuss the genesis of this, but okay. These rocks are typical of the end of the Archean. They are emplaced only at the transition between Archean and Proterozoic. So except if Muriel gives me time to speak until 7. No, bad joke, no. Okay, so just in order to summarize, in the Archean rocks, we have three main lithologies, three main components that are, and the more important are the granite from the basement, and after we have the greenstone, and of course the late granite. Of course, if you look at this, you will say, okay, but there is more than a few percent of greenstone here, if you look at the surface. But the greenstone are rocks, sediments, and placed at the surface. So maybe you have 2 or 3 kilometers of greenstones, but at depth you have 20 or 30 kilometers of gneisses. So the map is a representation of the surface, while this diagram are estimation of the volume. So this is why there is a difference. Okay, now we will look at these rocks and what kind of information they provide to us. First, I present you a nice river. The name of the river is Komatiite. It's in South Africa. And well, when you look at this river, you think that it should be very interesting to swim and to take a bath. But in the area, there are some animals that are not very, well, that can be dangerous. So these komatiites, the rocks that outcrops along this river, where they have been described, are ultramafic magma. So today, we do not know this kind of ultramafic magma. The ultramafic rocks that we know are nodule from the mantle. But these rocks are not lava. They are crystallized at depth from the magma ocean, and they remain like this. So these are lava, obviously, because we have this shape of pillow lava. These were lava. If the lava is placed underwater, you will have the pillow. If not, we can have lava flow just like here. This is from Canada. And typically, a lava flow contains at the basis cumulate. So these rocks with grain structures or texture is a cumulate. In upper level, we can find spinifex texture with olivine needles, just like here. So here, a microscopic view of these needles. And as everywhere in the world, at the top of the lava flow, we have some breccia. So again, pillow from Komatiite. And now if we look at these structures, this is something very strange to have these needles of olivine like this, while you know generally olivine is quite rounded or crystal and not a needle at all. So the name here is called spinifex, and spinifex in fact is this kind of plant that we can find in the African bush. And this plant contains some crystals of silica. And of course, this is very painful for this part of your leg when you walk in the bush. And when the geologists saw this olivine needles, the structure of the olivine needles remember them the structure of the leaves of this plant, so they give the name of the plant to the structure. Okay, this is not geology, but this is botanics. Okay, so if we look at this olivine crystal, so we have the crystal, but you can see in some places, so there is a main crystal, there are small crystals here or here. And if we look carefully, we can see that some crystals seems to be empty here and with a dendritic structure in many places. So this is quite typical of, let us say, rapid cooling of this material or rapid crystallization of this material. So just a comparison between modern lava from La Réunion Island, taken 5 years ago, and emitted 5 years ago, and Archean Komatiite from Canada with these needles. So I like this picture. This picture is not a Komatiite, but is water on a car, on the glass of a car, and it was frozen extremely rapidly. That was so it's a very big difference of temperature between the temperature of the water and the temperature of the air. And we can see that if water crystallizes rapidly, we can observe long needles of ice, and in some places this kind of dendritic structures, as we observe in speed effects. This is more or less the same as we can observe here. So it is generally concluded that this texture, speed effects, correspond to a very rapid crystallization of olivine and consequently a rapid cooling of the lava. So some modeling has been made, and here we have the solidus of, so this is a temperature pressure diagram, the solidus of the mantle. So on this side in green everything is solid. Here we have the liquidus, so what is this, yellow, everything is liquid, and in between we have crystal in equilibrium with liquid, and the degree of melting, the amount of liquid, is represented here. So if we look what happens today in mid-ocean ridge, we have uprising of rocks from the mantle and the underwent adiabatic melting. Oh. And the emplacement temperature is about 1,250 degrees. If now we look at the hotter lava in place today in hotspot, we have more or less the same thing, but at higher temperature, and the temperature of emplacement is around 1,400. The same calculation made for Komatiite result in temperature of emplacement of about 1,700. So this lava were hotter than the lava in place today. In a recent paper, Campbell and Griffith, so 2 years ago, report the analysis of rocks from different ages, and they consider this empirical equation that relate the temperature of crystallization to the magnesium content of the lava. And doing so, they can deduce the temperature of crystallization of the lava. And so they obtain this kind of thing, whereas today, in hotspot, the temperature of emplacement of the lava is between 1,350 and 1,450 degrees, while in the Archean, the temperature is between 1,600 and 1,700. So, and the change is more or less at the end of the Archean. So that means, and this is used as a very strong argument in favor of the fact that during the Archean, the internal heat production was greater than today. So this results in high degree of melting of the mantle, the genesis of ultramafic magma, and the emplacement of this magma at very high temperature. Since the Archean, the Earth cooled, and now the Earth is not able to produce so high temperature magma. So this is some proof that the Archean Earth was warmer, and that since the beginning, since its formation, it progressively cools. So, okay, here this is Earth's production in Earth. One is a today production. So this is a production from all the sources, and this one, I must admit that the color is not perfect for this, but that this one is heat produced by radioactivity. What we can see, for instance, is that at 4.0 billion years, the heat production was more or less 4 times the present day heat production. So this is something quite important. So if we look at these sources of energy, we can see that today this is more or less 42 terawatts. And this is produced mainly by disintegration of radioactive isotopes, more or less more than 75%. This is some residual heat of accretion, so the transformation of kinetic energy into thermic energy for a little bit more than 10%. This is a latent heat of crystallization of the liquid core. And the last one is heat due to the crustal tides. So the tide is affecting not only ocean but also the solid rocks, and the effect and the motion of the rocks can produce heat, and today this is 1% of the thermal budget. So what we can see is that all these sources are diminishing in course of time. For instance, the radioactive element, they produce heat because they decay, but the amount of radioactive element decrease, of course, in course of time. The same for the residual heat of accretion. So the Earth receives this heat at the beginning, and since the beginning, the Earth is lost this heat. So the amount of this heat decreases in time. The same for the crystallization of the core, and the same for the tide, because we have seen that the moon was closer to the Earth, so the tide were more important, and the heat provided by the tide was also more important than today. So what we see is that, okay, more or less all these sources were more efficient, more active in the Archean than today. And this is totally consistent with the decrease of heat production in Earth in course of time. This is consistent with that. So during a long period of time, there were two schools about Komatiite and about the depth of genesis of Komatiite. Some people say, no, Komatiite is very easy to generate quite near the surface. Okay, they say this, but it was difficult to explain the high temperature, but near the surface. And other people say, no, this is not true. Komatiite need to be generated at depth, very great depth in the mantle. And so recently, some people from, first there were people from Rennes University, they discovered diamond in Komatiite. So these are this kind of diamond. This is an industrial diamond. This is not you cannot put this kind of diamond on a ring, but there is diamond. So this is something important, because until now, people thought that diamond was present mainly in kimberlite. No, this is another kind of place where you can find diamond in Komatiite. And the second point is, of course, if there is diamond, that means that the genesis took place at depth. That the magma, or the rock that generates the magma, was coming from depth. And a more recent work by Cartini studied the isotopic fractionation of carbon in this diamond, and concludes that the depth of genesis was more than 300 kilometers. So I think we can say that the depth of genesis of this Komatiite is great depth. Oh, okay. So, sorry, this is in French. I will translate. Komatiite are ultramafic lava, so the silica content is quite low, and the magnesium content is high. The density is very high, and if you took a sample in your hand yesterday, you have seen that the density of these rocks is very high. It's about 3.2. They come from a high degree of melting of the mantle, more than 50%, 50 to 60%, while today the basalts in mid-oceanic ridges or basalts in hotspot are generally produced by 20 to 30% melting of the mantle. Here the degree of melting is by far greater. Temperature of emplacement is high, and the depth of genesis is also a great depth because this is demonstrated by the presence of diamond. And something important is that Komatiite existed only in Archean terrains. We do not know more recent Komatiite. So the presence of Komatiite strongly militates in favor of a hot earth or internal earth during Archean times. Now we will have a look at the continental crust. So we had a look on the Komatiite. Now we'll look at the granitogneissic basement. So remember, these rocks are gray gneisses here, or here, so it's a gray gneisses. And looking at this rock, these rocks at microscope, we do not discover a lot of minerals. They are mainly made of quartz, plagioclase feldspar, biotite, and sometimes some epidote. And all these rocks have the same composition. If we plot this rock in a diagram for here is quartz, alkali feldspar, and plagioclase, they fall here in a domain whose name is tonalite and granodiorite. So these rocks are not true granites. The granite should plot somewhere here with K feldspar. There is no K feldspar in these rocks. So they are tonalite and granodiorite. And now if we look at not boxes for the name of the rock, but at evolutional trends, there are here tolitic trend, alkaline trend, and here three trends that are calc-alkaline, K2O poor, K2O intermediate, and K2O rich. So obviously these rocks belong to trend of differentiation of K2O poor calc-alkaline magma. Now, if we look more in details, we can see here is anorthite is a calcic plagioclase, albite is sodic plagioclase, orthoclase is potassium feldspar. And in this diagram, we can find some fields, granite here with orthoclase, granodiorite, tonalite, and trondhjemite, that is the same, which has the same plagioclase as in tonalite, but plagioclase richer in albite, in sodium. So, if we plot Archean gray gneisses in this diagram, we will obtain not evolution trend, but this kind of group of data. Maybe you do not realize, but in this diagram there is 1,350 points. So all points are one over the other and so on. So that means that the composition of the rocks is very constant, very concentrated. There is no big variety in these rocks. They have all the same composition. So looking at the picture of the field, we had the same impression that everywhere in the world the rocks were similar. If we look at chemical composition, they all have strictly the same composition. So this is something important. Another important point is that they fall in the field of trondhjemite, tonalite, and granodiorite. So they are called TTG. Geologists are generally lazy person. And so if you have to say tonalite, trondhjemite, granodiorite, it's very long, so we use TTG. So now I will speak about TTG when I will refer to this kind of rock. A last point with this figure is that here in green, pale green, is the composition of the modern continental crust. When I say modern, I say younger than 2.5 billion years, so Proterozoic and today. And obviously, the composition of the modern crust is granodiorite to granite. So the composition of the modern crust is different from the composition of the Archean crust. So that means that if the composition is different, that means that the source for the Archean crust is not the same as for the modern crust, or that the mechanism of genesis were different, or as often in geology, that both sources and mechanism were different. But this diagram shows this difference. Another point of comparison is this diagram, potassium, sodium, calcium. So here are the Archean TTG. Here is a calc-alkaline differentiation trend. And what we can see, there is no trend, no differentiation trend. And the Archean rocks do not plot on calc-alkaline differentiation trend. If we compare with the modern crust, here are points for the modern continental crust. We can see that this modern continental crust defines a trend of differentiation and that these trends follow the calc-alkaline trend. If you want to remember something simple, we can say that the Archean crust is mainly sodic, while the modern crust evolves toward potassium and nothing near sodium. So this is one of the main differences. Sodium rich for the Archean crust and potassium rich for the modern crust. Now if we enter into the intimacy of these rocks, if we look at some trace elements, just like rare earths, we can see also very strong differences. Very strong differences because the pattern for the rare earths are the same for light rare earths, but with a very strong difference for the heavy rare earths. The scale is the same for the two diagrams. And the Archean rocks are very poor in heavy rare earths, while the modern rocks are richer in heavy rare earths. And in addition, there is a negative, very often a negative europium, negative europium anomaly in modern rocks, and nothing in the Archean rocks. So we'll see how to interpret this. Okay, if we look at if we take a massif of this, for instance, we go, I don't know where in Finland, for instance, if you want, we look at this TTG, and if we make some analysis, we plot the analysis in a diagram using silica as index of differentiation, we can see that we have trends of differentiation. So as differentiation proceeds, silica increase, and there is variation in element, and they more or less plot along a correlation line. So what is the origin for that, for these trends? What is the mechanism? So we can use this kind of diagram, where we plot here a compatible element, strongly compatible, and here a strongly incompatible element. And in this kind of diagram, partial melting will give a more or less horizontal trend, and fractional crystallization, a vertical trend. So obviously the trend is more vertical than horizontal. So that means that this trend of differentiation are due to fractional crystallization. If you are not convinced by this, in the TTG we can find crystals, just like this crystal, with zone crystals. That means that this crystal, during its growth, adapt its composition to the composition of the magma, and as the composition of the magma was changing, we have different zones like this. So if the composition of the magma is changing in course of differentiation, this is due to fractional crystallization. So this is a petrographic proof for fractional crystallization. So, okay, this is very interesting. There was fractional crystallization. But fractional crystallization, what is this process? We take a magma and we crystallize some minerals in the magma. But the important problem is not this. The important problem is what is the origin of the magma that subsequently will crystallize. So, if we look at isotopic diagram, for instance, here with neodymium, strontium here, neodymium, hafnium here, we can, in green here, is the mantle array, the composition of the mantle, and here is the composition of the continental crust. The Archean TTG that we study plot here in the mantle array. They have nothing to see with the continental crust. So that means that they cannot be derived by remelting of older continental crust. They must have an origin somewhere in the mantle. This origin can be in direct melting of the mantle or indirect melting of the mantle, but it is clear that this kind of diagram precludes an origin by melting of older continental crust. So we will try to explain the genesis of this TTG by melting of the mantle. Okay, so here is the modeling, geochemical modeling. We start with this composition, that is a chondritic mantle, here. And using melting equations, we will try to obtain this kind of liquid, that is a TTG. So here, again, the color is not perfect, but this composition, this one is for 1% melting of the mantle, and this one for 25% melting. So this means that the domain in green here corresponds to liquid produced by 1 to 25% melting of the mantle. Obviously, this can work with very low degrees of melting for light rare earths, but this doesn't work for heavy rare earths. So, okay, you know a little bit about geology, and we'll say yes. But if we are in the subduction zone, the composition of the mantle is modified by the fluids coming from the hydration of the subducted slab. So if we start with a mantle like this, and if we provide elements carried by the fluids, we can see that this fluid will carry a lot of lanthanum, but nothing about ytterbium. So they will not modify the content, the ytterbium content in the mantle. And unfortunately, the problem that we have here is a problem with ytterbium. So even if we modify the composition of the mantle with fluids, we will not modify the heavy rare earth budget. So this means that we cannot produce TTG by melting of the mantle. Any kind of mantle will not work. So we are a little bit disappointed, and we say we'll try model, not a direct melting of the mantle, but indirect melting. That means, for instance, today you produce a basalt by melting of the mantle in a ridge, and you will melt this basalt in subduction zone. So this is a two-step genesis. So we took here an average composition for Archean basalt, tonitic basalt. We'll try to reproduce this pattern for TTG. And if, a basalt that enters in subduction is transformed into amphibolite, garnet-bearing amphibolite, and after eclogite. So if we take the beginning of the process with a garnet-free amphibolite, we see that this works perfectly for light rare earths, but fails for the heavy rare earths. And so finally, the only model that can account for light and heavy rare earths is the melting of a basalt transformed into garnet-bearing amphibolite. So this is something very important. So the source for Archean TTG must be melting of a basalt transformed into garnet-bearing amphibolite. And the point, extremely important, is that we need garnet and hornblende in the residue of melting. This is what is said by this modeling. So, okay, we need garnet and hornblende. So, we can propose the model in 3 stages. The first one is melting of the mantle to produce a basalt. The second step is melting of the basalt to generate tonalitic magma with a residue with hornblende and garnet. And finally, some fractional crystallization to give the suite of TTG magma. Okay, so you will say, okay, but this is some kind of game. We play with some geochemical equation, we input some partition coefficient and so on, but this is a game of geochemists. So there is another possibility, that is to take a sample of basalt and to melt this sample of basalt to see what is the composition of the liquid. This is not theoretical, but this will be real melting. So I just show a picture of the press that we use in Clermont-Ferrand for this. And when we melt a basalt, we obtain liquids with composition of tonalite, trondhjemite, and some granodiorite, so similar to Archean TTG. They are rich in sodium, no affinity for calc-alkaline trend. And something maybe more interesting. When we look at rare earths, here are the composition of the sources, here and here. If melting takes place without garnet in the residue, the liquids are rich in light rare earths, but they are not impoverished in heavy rare earths. And this is only when garnet is stable in the residue of melting that we obtain this kind of patterns. These are similar to TTG1. So now we have two kinds of arguments. We have geochemical modeling and we have real melting, experimental melting of basalt that converge to the same conclusion. That is that TTG can be generated by melting of basalt transformed into garnet-bearing amphibolite, because we need amphibolite and garnet in the residue. Okay. So now if we look at the places where continental crust is generated, what happens to this basalt? Here we generate basalt, and of course these basalt are hydrothermally weathered, altered. They interact with water, and some minerals just like pyroxene, olivine, are transformed into serpentine, talc, and chlorite, and so on. So the first point is that when it is generated here, its composition changes, and the basalt incorporate water in the structure of minerals. The average age of the oceanic crust when it enters in subduction, I say the average, the mean age, is 60 million years. So that means that this crust, when it will move at the bottom of the ocean during 60 million years, will cool and it will become very cold. So when it will enter in subduction here, this will correspond to introducing a cold slice of rock into a hot mantle. And this is what we see generally in this kind of diagram, where we see that the isotherms here, we see the cold slab entering into the mantle. So subduction of oceanic crust corresponds to introducing cold basalt into a warm mantle. So the geothermal gradients along the Benioff plane here, the geothermal gradients are very low due to these relationships. So if we look now at diagram with temperature and depth here. Here is anhydrous, the dry solidus for basalt, and here is a wet solidus for basalt. So, as we have seen this morning, water significantly decreases the temperature of melting of rocks. Now we can draw this line of stability of hornblende, of amphibole. So amphibole is stable on the left and not no more stable on the right. Here is the line for garnet. Garnet is stable at high pressure and not stable at low pressure. So that means that this field here is the only place in that diagram where we can find together garnet, amphibole, and liquid. Liquid produced by melting of the basalt. So the TTG were generated somewhere in this place, because this is the only place where we can fulfill all the constraints, melting of a basalt, amphibole, and garnet stable in the residue. So TTG were generated somewhere here. Today, as I told you, in the subduction zone, we introduce something very cold in the mantle. So the geothermal gradient along the Benioff plane are very low, just like this one. And first conclusion, this geothermal gradient doesn't cut this field. So impossible to generate TTG from this process. In addition, if now we show here some curves of dehydration of the subducted slab. So we have seen that the basalt of the oceanic crust change its composition. When it is generated, it consists in olivine, pyroxene, which are anhydrous minerals, and by reaction with water, it will produce hydrous minerals, just like amphibole, serpentine, epidote, and so on. So what we see here, if we follow this geothermal gradient, we will first cut the reaction of dehydration. So this one is for anticorite, chloride, talc, zoisite, tremolite, and so on. Well, no matter the name. So that means that the slab will dehydrate before to reach the temperature of hydrosmelting. So when the slab will reach the temperature of 700 or 800 degrees here, there is no more water in the system. And the temperature of melting is somewhere here, more than 1,400 degrees. So that means that the subducted slab today in a normal subduction zone doesn't melt. It returns at depth in the mantle, so it only dehydrates here. And the water liberated by this reaction will induce the melting of the mantle here. So the source of the calc-alkaline magma in subduction zone today is the mantle transformed by the fluids coming from the dehydration of the slab. So no chance to melt the basalt, the subducted basalt, today in subduction zone. If now we know that in the Archean time we were crossing this domain, so we can propose higher geothermal gradient. This is not totally stupid because we have seen with Komatiite that the Earth was warmer during Archean time. The heat production was greater and the Earth was warmer. So it's not stupid to propose that during Archean times we had higher geothermal gradient. So this geothermal gradient, okay, is cutting the green domain. But if we follow this gradient here, we see that excepted one dehydration reaction, this is a destabilization of anticorite, we will cross the temperature of hydrosmelting before dehydration. So when we will reach this temperature of 600 or 700 degrees, there is still water in the basalt. So if there is basalt, if there is water, the basalt can melt. So we propose that it was possible to melt the basalt in Archean times because due to higher geothermal gradient, just like here. And in the Archean, the source is not the mantle as today, but is the subducted basalt itself. So we have a source that is a different source than today, which accounts for the difference of composition of the modern and Archean continental crust. You see that, in fact, this is only the relative position of dehydration and melting curves that are changed. Today, we cross first dehydration before to reach hydrous melting, while in the Archean, we first melt and the position of the dehydration curves is at higher temperature. Okay, so some summary. TTG are tonalite, tronzemite, and granodiorite. They are generated by melting of hydrous basalt in garnet and hornblende stability field. Melting can take place in the subduction zone, and in this case, this is the oceanic subducted crust that melts. And TTG exists only in the Archean. This is consistent with what we have seen for Komatiite. TTG require high geothermal gradient, so require high heat production from the internal Earth. And so, at the end of the Archean, the Earth has cooled too much and was after unable to generate this TTG. So, okay. After the Archean, the Earth was too cold and cannot generate TTG. But we can push a little bit more the discussion. So we have seen here that subduction is introducing something cold into the mantle. We introduce something cold because, in average, the oceanic crust moved at the bottom of the ocean during 60 million years. So it has a lot of time for cooling. Now, if we imagine that we do not subduct a very old crust, but a very young crust. That means that, for instance, the crust was at the bottom of the ocean only during 5 or 10 million years. This will correspond to introducing something not so cold, so maybe warm, into the mantle. So the thermal regime, principally along the Benioff plane, will change. And for instance, if there is some modeling that has been calculated for subduction of oceanic crust whose age is 200 million years. Here is a gradient for 50, 30, 20, 10, and 5 million years. So that means that younger the crust, warmer or hotter the subduction. So if today we can subduct somewhere a very young oceanic crust, we could expect to see magmas with the same composition as Archean magmas. And of course, if I speak about this, the situation exists. And there is a very nice place in South America where we have 3 plates. Here is a South American plate, here is a Nazca plate, and here is the Antarctic plate. So today, if we look at adacites, there are adacites in the world. Of course, we have seen here this beautiful place in Patagonia. But there is here in Ecuador, where the Carnegie Ridge is subducted. There is in Panama, Baja California, in Cascade, St. Helens is adacitic volcanoes. There are here in Aleutian Islands, and here is Adak Island. The name of Adakite is coming from Adak Island. There are in Japan, in Kamchatka, Japan, Philippines, and also in Papua New Guinea. So there are adacites all around the world. And if we plot in this diagram the content of magma in heavy rare earths, and here is the age of the oceanic crust when it enters its subduction. When the subducted crust is younger than 30 million years, the ytterbium content is low and consistent with melting of basalt, of subducted basalt. And when the crust is old, the ytterbium content is very high and consistent with melting of the mantle wedge. So it seems that what we have seen in Patagonia can be generalized to all the adacites and all the calc-alkaline magma in the world today. Okay, now we'll change the topic. There is a big problem. That is that I present you this genesis of TTG in a plate tectonic model. But a few years ago, and that was worse when I started to work on this kind of rock, people think that there was no plate tectonic in Archean rocks. So, okay, there was some model of vertical tectonics, plume-driven models of plate, model of delamination, and the model that I present to you. In fact, all these kind of models can be summarized in 2 kinds. One is just like plate tectonics here, and another one is purely vertical, so that means gravity-driven, and with mantle plumes. For instance, here the basalt melting takes place in the subducted slab, and here these are underplated basalts that melt due to the plume activity. So what is important is that in this kind of model, there is no need for plate tectonics. So the question is, does it exist plate tectonics during Archean times? What are the markers for plate tectonic? So here is not Archean, these are the Alps. And what we see in the Alps, you know, plate tectonics, you move plates horizontally. So if they collide, if they enter in collision, it will result very flat structures, thrusting like here. So this kind of thrust of flat structure, horizontal structure, are typical of plate tectonics. Of course, when 2 continental plates enter into collision, they will form mountain chain, and that will result in crustal thickening of the crust here. And another argument could be the existence of ophiolite. And mainly in ophiolite, of course, you have the basalts here, and you have the dike complex here. And the dike complex, of course, proves that something is opening and that there are horizontal movement at this level here. So if we look at Archean terrains, here is the seismic cross-section in Canada, in Abitibi area. And here is the interpretation of the seismic profile. This is in late Archean terrains at 2.5 billion years. We see a lot of horizontal structure here that are interpreted by Canadian geologists and geophysicists as thrusting. And also, there is something that is a remnant of the subducted crust. So here in Canada, at 2.7, I think there is no problem. There was plate tectonic. Now, if we look, if we look at another place, this is Limpopo belt between the Cape Val Craton here in South Africa and here the Zimbabwe Craton. So the age is 3.0. And we also have very big thrust like this. So very big horizontal structure consistent with plate tectonics. The same has been described here in older terrains in the Barberton. There are some, so it was refolded, but there are also some big thrusting. This kind of thrusting has also been described in Baltic Shield, and some people describe in Greenland and in many places. So, okay, there are horizontal structure. Another argument is based on a study of the association between amphibole and garnet here. And using this as a barometer, the people who study this conclude that the pressure of emplacement of these rocks was about 14 or 15 kilobars, so that means 45 kilometers thickness, which for the Archean crust could represent crustal thickening. So they conclude that we have crustal thickening at 3.2 here in this rock. Another argument are these folds in Isua. So we are 3.8 billion years. There are this kind of folds that are typical of thrusting folds. But also, some geologists consider that they discover there the oldest ophiolite in the world. So this ophiolite consists in pillow lava here, but in a dike complex where dikes are emplaced one into the other, just like here or just like here. So if we put all this argument together, great horizontal structure, crustal thickening, dike complex, obviously there was plate tectonic during the Archean. So probably you ask to use the question why I insist so much on this aspect. I insist so much because when you arrive on Archean rocks, the first thing that you see is not plate tectonics, it's not horizontal tectonics, but vertical tectonics. The first thing that you see is that. And you must look carefully to see this thrust and this crustal thickening and so on. We have seen here that in the Pilbara Craton in Australia, we have these domes here of granitic gneiss, and we have the greenstone in between. This kind of structure was studied in India, in Olivarsipur, and right? We will survive. Where we have these domes here. We can see the structure of the dome, and the greenstone is in between the domes. And if we look at this kind of diagram in 3D, we can see that the dome are ascending and the greenstone are sinking into the gneisses. So this results in vertical structure. And this kind of vertical structure can be driven only by gravity forces. This kind of structure is called subduction here. So what is the source of subduction is known only in Archean terrains. In fact, this is something very simple. If we take here continental crust, so with a low density, 2.7, and if we emplace above this continental crust komatiite, if we emplace komatiite, the density of komatiite is very high. So we create some inverse density gradient, something very dense above low density rocks. And the high density rocks will sink progressively into, here we see, one more, okay, will sink into the crust. So if this sinks, we have up rising of the rocks of the continental crust. And these are the structures that we see first when we arrive in Archean terrains. And in fact, the opinion now for geologists is that in the Archean, in the old time, we think in the Archean no plate tectonic, after Archean plate tectonics. In fact, now the idea is that during the Archean there were two kinds of tectonics, plate tectonics and subduction. And after the Archean, subduction stopped and only the plate tectonic remains. So that means that you imagine that this kind of structure can take place only in the middle of a plate, only in the middle of the continental plate. We need to have a strong contrast of density in order to generate, to initiate and to generate this kind of structure. So we need to emplace very heavy rocks above low density rocks. So this can take place only in the middle of the plate. So geologists consider that in the Archean, at the limit of the plate, just like today, we had subduction, we had opening in mid-ocean ridge and so on, just like today. But in addition, in the middle of the plate, we had this kind of structure. And this kind of structure can take place only in continental plates, in continental blocks. This kind of structure disappears at the end of the Archean. Why? Because at the end of the Archean, the Earth was cold and not able to generate komatiite. So if there is no komatiite, there is no strong contrast of density, and the process stops. So consequently, this change in tectonic style is also a consequence of the cooling of the Earth, due to the fact that the Earth do not produce anymore this kind of magma. If you emplace a basalt with a lower density above continental crust, you will not initiate the subduction. So this is possible only if you have komatiite. So just I will finish now with this aspect. It's that, okay, there was plate tectonic, but the plate tectonic was slightly different than plate tectonic today. For instance, if we consider that at 4 billion years, the internal heat production was 4 times greater than today. What we know is that this internal heat was released somewhere. Because if not, if heat accumulated in the Earth, we should have a general melting of the mantle. So this is not the case. We had general melting of the mantle very early during the magmatic ocean episode, but after, nothing. So that means that this heat was evacuated somewhere. If now we look the place where heat, internal heat is evacuated today, it is evacuated in ridge system. You can see here is a heat flux at the surface of the Earth. So we see that in the middle of the plate, the heat flux is very low, but in the oceanic ridge, due to the convection, we have a very high heat production. So most of the internal heat is evacuated in the ridge system. So, okay, this is not a beautiful, this is a heat flux here. Here is the ridge, and of course, the flux decreases very rapidly when we go far from the ridge. But this heat is evacuated by volcanism at the ridge, and also by something that is linked to volcanism, by hydrothermalism. The black and white smoker, the water is quite hot and helps in evacuating, in releasing the internal heat of the Earth. Okay, so if there is more heat to evacuate, we have several possibilities, but one is to have a more efficient convection, so plate motion more rapid, but we cannot we can imagine plates moving at some rate, but not strong rate. And another possibility is to increase the length of the ridge. If we have more heat to evacuate, we can do this by increasing the length of the ridge. So there is an empirical equation that gives, here is the amount of heat to evacuate, here is the surface of the planet, and here is the length of the ridge. If we consider, which is we realistic assumption that the volume and the surface of the Earth didn't change. So we can say that the amount of heat to evacuate is correlated to the length to the cubic root of the length of the ridge. So for instance, if we have three more times heat to evacuate, the length of the ridge should be 27 times longer than today. So the consequence is that today we have plates like here, and the typical size is some 1,000 kilometers for the plates. In the Archean, if we consider that the ridge system was longer, this should have resulted in smaller plates. If the volume of the Earth is constant, if you increase the length of the ridge, you should have smaller plates, just like what we see here. So the size should be some 100 kilometers and not 1,000 kilometers. So maybe we can just look at another place, which is pleasant if you drink some rum. This is the Fiji island. And this is the North Fiji basin. So we have here Fiji Island, New Caledonia, Vanuatu here. And the North Fiji basin is somewhere here. So here is the Pacific plate, here is the Australian plate. And this place in the world is a place where on a very big surface, the heat flux is maximum on modern Earth. So here is the heat flux, and it is very high in the whole Fiji basin. So in other words, this is a place where our planet has to evacuate a lot of heat. This is a place on Earth where today a maximum heat is evacuated by our planet. So it is interesting to see how our planet proceeds to do this today. And what we see is that the length of the ridge in red here is very long. If we make the ratio between the surface and the length of the ridge, in this North Fiji basin, the length of the ridge is 20 times greater than in the other places in the Pacific Ocean. So the length of the ridge is very high. So that means more heat to evacuate, longer ridges. But you see also that if we have a long ridge, we have microplates. And we found in this place microplates. So that means that the assumption that during the Archean, if the heat flux was greater, a way for evacuating this heat would be to produce longer ridge, and the consequence would be smaller plates. So maybe as this is the case in the North Fiji basin, maybe the assumption is not so stupid. Another point interesting is that if you increase the length of the ridge, you will increase the amount of black and white smoker and of hydrothermal vents. And we have seen that in Archean terrains, there is a very high, huge quantity of this system, of this chert. There is more cherts than today. So this is consistent with a longer ridge system. Okay, just for fun, and I finish with that. Of course, if the plates are smaller, they will enter in subduction earlier, so we will subduct young crust. Young crust means that the crust has not a very high density, and so it will more or less float, and the buoyancy will result in a flat subduction or low angle subduction here. So more flat subduction than today. Okay, this is the end. So during the Archean, the plates were probably smaller. Maybe if convection is slightly more efficient, can be more rapid. Flat subduction or low angle subduction. Of course, one of the big differences is that contrarily to today, this is the subducted basalt that melt to generate the continental crust. And of course, if we have a greater length of ridge, this will be in favor of more hydrothermalism in these systems. Okay,